We just have been talking about dealing with uncertainty in our measurements. And when we are dealing with large sets of data, then it becomes pretty unmanageable to propagate the uncertainty for them. So instead, we need to use a different strategy. And the way that we're going to do that is we're going to use some statistical methods. Now, if you've had other statistics classes, then most of this is probably going to seem pretty familiar. But for those of you who, like me, maybe didn't get into statistics until you got into chemistry, we're going to go ahead and start with some basics. So one of the most common ways that we look at statistics is we look at measurements over time. And what we find is that of all of the measurements that we get, if we track the frequency, and then we look at each individual measurement, those are all on the x-axis. So let's say I am measuring the mass of pennies before 1980. And so when I'm looking at the masses, I'm going to have a little bit of spread in the masses of a bunch of different pennies. And so what we find, though, is that many of them are the same value, and then the frequency with which we find some of the other values goes down as we go further away from the most common number. Okay, so this is our most common measurement. And if we take an infinite number of measurements, obviously that's not possible, then that is this overall kind of bell curve shape is able to be expressed using the Gaussian mathematical function. And the Gaussian mathematical function has the form, you don't have to memorize this or anything, but I just want you to look at it. 1 over sigma square root 2 pi multiplied by an exponential function of x minus mu quantity squared over 2 sigma squared. And of course, x is this axis, and mu is this value in the middle here. Sorry, it's going to be a little squeezy there. So mu is defined as the mean, and everybody has already calculated the average. For a non-infinite set, you might be familiar with the x bar notation for calculating the average. And if I put this into mathematical terms, you already know that we take all of our different measurements, which I'm going to label x sub I. So all of our measurements are labeled x1, x2, x3, x4, all the way up to xn. We add them all together and we divide by n, which is the number of data points that we have. And this is our average. And statistically, we call it the mean. So sigma is called the standard deviation. And we're going to look at the mathematical part of that as well. But again, since we're never able to work with infinite sets, we're going to go ahead and use the notation for the non-infinite set. So just as x bar is our non-infinite set notation for an average, lowercase s is our notation for a non-infinite standard deviation calculation. So the standard deviation, if you think about what the words are saying there, we're talking about how much do the values deviate. And when we talk about them deviating, we're really talking about how much they deviate from that average. So when we calculate that standard deviation, we are going to take each of our individual measurements, those were xi, we're going to subtract whatever the average value is. This could be positive or negative, and we don't want any negative numbers because we're going to add them together. So we're going to square them before we add them. And then we're going to add all of them up. We're going to take each of our data measurements, and we're going to take the difference between that value and the mean, square it, add them together, divide by n minus 1, and then we're going to take the square root. If we did not take the square root, then this would be called the variance. S squared is just the variance. And n minus 1 is also called the degrees of freedom. And we're going to be using this term quite a bit. So sometimes we will also write DOF just for short. Okay, so we can calculate the standard deviation, we can calculate the mean, and both of these are pretty straightforward. So we're going to go ahead and practice those. I'm going to switch on over to Excel here really quick and show you how we can calculate the average and the standard deviation a little bit faster than doing it by hand. But first, I'm just going to have you go ahead and calculate some things by hand. So let's imagine a situation where, a situation where we've done some titrations. And we've done some titrations to standardize a solution. And when we standardize a solution, we're comparing our unknown solution to a known, a standard, to figure out what the real concentration is. So let's say that we standardized, or we did a bunch of titrations. And so now we have a bunch of data. And I'm just going to give you some made-up numbers here, imagining that we have done 6 titrations. Oops. That's what happens when I try and talk and write at the same time. Okay, so we have 6 molarity measurements that we're going to do. We're going to calculate the average, and we're going to calculate not the sigma, we don't have an infinite data set, the standard deviation. So go ahead and pause the video right now and go ahead and calculate the mean and the standard deviation. Okay, so hopefully you were able to do that calculation and you got 0.06318, and I'm going to go ahead and subscript the next number, 5. And then the standard deviation, I got 6.28 times 10 to the minus 5 molar. So here's a quick reminder that the standard deviation is looking at measurements of real numbers, and so it always has units. This is something that often people tend to forget, and it's going to have the same units as whatever the mean is. All right. So when we look at the significant digits on this, with the scientific notation, it can be a little bit hard to figure that out. So let's go ahead and rewrite this standard deviation, 0.1234628. Okay, so if we wanted to look at the significant digits here, if we're using our standard deviation like uncertainty, then we probably are going to keep this first non-zero digit, and then we're probably going to round and subscript these other digits. Oop, not both of them. Just subscript 1. So if we look at the decimal places, 1, 2, 3, 4, 5 over, 1, 2, 3, 4, 5. This 6 lines up in the same column as the 8, which seems pretty reasonable. So if we were being consistent between these two numbers, we probably would write the standard deviation is 0.00063 molar in order to match the mean. Now, if you calculated this by hand and you thought, oh my gosh, this is super tedious, I totally understand, and I have great news for you, which is that when we do these calculations, we're almost never going to calculate them by hand. I mean, maybe we'll calculate the mean because it's not all that difficult, but we have tools for that. So we're going to go ahead and switch over to Microsoft Excel, and I'm going to show you how to do this calculation in Excel if you have not done it before. Okay, so I took a minute before class here to enter in one of the columns all of the molarity values. Now, normally I would probably write molar units in as well, just for labels. I like to label my columns. And so I'm going to go ahead and calculate the average here. This is easily accomplished. If you haven't used Excel before, I can give you some Excel tutorial videos to watch, or we can meet and we can do it together one-on-one. So anytime you want Excel to do an equation, you type the equals sign, and then there are a ton of different programs that are already set in Excel. So average is one of ours. And so I'm going to calculate average, and then it gives me this parentheses. I'm going to select, so that's me clicking and dragging to select all of the 6 numbers, and parentheses, and hit enter, and that has calculated the average for me. If you want more or fewer significant digits, you do that up here where you can. It's telling me that I can't change the number. Okay, maybe it doesn't have enough space. I'm going to tell it this is a number, and we can increase as many significant digits as we want. Of course, that doesn't mean that they are significant, so we'll go ahead and keep it the way that it was before. Now, when we calculate the standard deviation, we don't have to do that by hand because Excel has it. So we just, again, hit equals sign, and then STD. This STDEV is one that we have. The other ones that you can look at here, there's a whole bunch, right? So let's take a look at them. STDEV of all of these numbers. This gets the number that matches up the one that we did. So let's look at the other ones real quick and figure out what's going on. All right, so this dot P, if I calculate that, what's happening is in some standard deviation calculations, here they divided by n instead of n minus 1. Okay, so that's a slightly different standard deviation. It's not the one that we want. And this STDEV.S is the other one that looks kind of like it. Let's calculate that real quick. And it happens to be exactly the same as the STDEV. So you can use either one of those, just don't do the P. And if you forget which one, then calculate all of them. The smallest one is not the one that you want. All right, so I'm going to switch back over, and we're going to go ahead and, actually no, I'm not going to switch over. I'm going to give you some practice. The practice is going to be on these equilibrium constant data that I had my physical chemistry class calculate at 25 degrees C, and they just happen to have a bunch of different numbers, right? So these first 4 were all 1 year, and then these 2 were from another year, and then each of these were from 2 different years as well. So anyway, let's just go ahead and calculate the average and calculate the standard deviation. For both of these, you can go ahead and pause the video and go ahead and calculate the average and standard deviation. Okay, so when you calculate these, I am sure that you probably are going to get exactly the same things that I am. But what we can do here is a little bit more. Because let's have a conversation about significant digits. Also, one more conversation about Excel. If you notice that your Excel column isn't quite the right width, you can go up here to where the column label is and double click it, and it will automatically adjust the width to whatever your widest thing is on Excel. Okay, now we're going to go back over to OneNote, and we're going to go ahead and talk a little bit about standard deviations for the numbers that we found here, and think about significant digits and how we might want to report them. So the numbers that we just got, the average was 1.30 times 10 to the minus 4 molar units, or excuse me, there are no units on K. And then the standard deviation said 7.79 times 10 to the minus 5. So if we think about sig figs here, our standard deviation usually gives us some clue about how many significant digits we should keep. So 1, 2, 3, 4, 7, 7, 9. Usually with our standard deviation, we're only going to keep that first digit. So if we think about the average, that would be 0, 0, 0, 1, 3, 0. So our significant digits, the last significant digit, or the last major digit that we should keep, is probably this one, if we are using standard deviations. So if I'm only using standard deviations to report the mean, I'm probably going to say 1.30 times 10 to the minus 4th, and the standard deviation I'm going to say is 7.8 times 10 to the minus 5. However, standard deviation is not automatically what we want to use in order to report uncertainty. So first, we need to think about what standard deviation actually is. So let's go over for a second and look at our Gaussian curve again. Figure 4.3 from the Harris text shows us how the standard deviations fit into a Gaussian curve. So plus or minus 1 standard deviation just means that we're considering the middle fraction of the curve only. And what percentage is this? We can actually find this in table 4.1. And table 4.1 is kind of oblique. It's hard to interpret, so I'm going to go ahead and do some interpretation of it for you. All right, so I want to just reiterate the Gaussian function for you for just a moment. Remember that we wrote it 1 over sigma square root of 2 pi e to the minus x minus mu quantity squared over 2 sigma squared. And in this table, the function that is actually graphed is 1 over square root of 2 pi e to the minus z, not x, z squared over 2. And that's because they have defined for this function x minus mu over sigma was equal to z. Okay, so let's go back over to table 4 for just a second. The first thing that I want you to notice here is that this curve says that it's the normal Gaussian error curve. That means that the whole area for the entire function is set as equal to 1. And that the z value of 0 means that we're right in the middle of our curve at x is equal to 0. So I'm going to show you that again in figure, I think it was, 4.3. Okay, so there's the x equals 0 in figure 4.3. And then we can see where the 1, 2, and 3 and the minus 1, 2, and minus 3 significant, standard deviations are away from that 0. So switching back now to table 4.1 again. Okay, look down the left-hand column of z and notice where it has 1.0. That's 1 standard deviation. And the area right there is 0.3413. So in the figure 4.3, that means that plus or minus 1 standard deviation contains 2 times 0.3413 times 100%, which is 68.26% of the curve. So go ahead and pause the video for a second on table 4.1 and calculate how much area is contained in plus or minus 2 sigma. You should have found that this area is 95.46% of the total area of the curve. And it's pretty common for us to hear people talking about the number of standard deviations away from the mean something is. That's kind of generic. But the standard deviation allows us to describe more than just like what portion of the total area something is. It also tells us about precision. So for this, we're going to switch over to figure 4.2. I know this is going back from figure 4.3, but I can't help the order that they talked about them in the book. So what you should have taken from figure 4.2 is that the more precise the measurements, the smaller the standard deviation. So this is really awesome because this allows us to actually quantitatively measure standard deviation. We look at our measurements, precision. We can use standard deviation to tell us how precise something is. The smaller the standard deviation, the more precise a measurement is. So now's a good time to take a break, and we'll do assignment number 3, which will let you practice a few of these concepts. So I would like you to do problems 4.1, 4.2, just parts A and E. I don't think you need to do 4 of those or 5 of those. Problem 4.3 and problem 4.4, parts A and B.